Swayam Prabha. Digital India. Educated India.
We have seen that creep is basically time, temperature and activation energy controlled process, and it happens at a constant stress, typically below the yield strength. So, there is a difference between the consideration of the stress being maintained below the yield strength, and see normally when we design a high temperature let us say boiler or an engine cylinder and things like that, it is subjected to lot of internal stress as well as temperature. And now in spite of being below the yield strength, supposing one has used an yield limited design, let us say one has designed a boiler for example to consider yielding and fatigue related issues, let us say leak before break type of a paradigm. Still it is not enough to design let us say pressure vessel based on these two considerations. One has to look at the creep related issues also, because even if the material is below the yield strength during operation, since it is working at a high temperature for prolonged periods of time, it can still undergo significant amount of creep strain. And what is significant amount of creep strain depends upon how much of strain would be permissible, how much of strain would not interfere adversely with the functioning of that high temperature pressure vessel or high temperature equipment is something that one has to decide. So, we look at the mechanical behavior of the material under creep conditions. So, creep is basically a phenomenon that occurs below the yield strength. So, you might not have stressed the material beyond the yield strength, but the mechanisms which operate are time, temperature and activation energy dependent. Basically diffusion is the rate controlling mechanism. So, it has nothing to do really with the dislocation moment. When you talk about yielding, the yielding is something that occurs when the dislocations just start moving, but here there is nothing like dislocation movement. The creep will take place purely governed by diffusion. So, that is where the strain can occur even below the yield strength of the material. So, now if you subject to the material to some stress, so this sigma can be much lower than the yield strength, and then you maintain it for a sufficiently long time. So, your stress pulse is something like this instantaneous rise to its working stress, then hold it for a long time and then bring it back to zero stress instantaneously. The strain response is relatively lax in the sense it lags in terms of time. So, to get this in fact the strain to fully develop, it takes a significant amount of time, and then when you unload, again there is some instantaneous unloading. Just as you have some instantaneous strain here during loading, there is an instantaneous unloading strain, following which this slowly comes settles to a permanent strain or permanent deformation, and that is where it becomes a little objectionable, because even if you have not reached the yield strength, still because of holding the material at a long temperature for a long time at a high temperature under certain working stress, you have some permanent deformation in the material. So, this creep is a very different phenomenon compared to our usual phenomena of yielding and plastic deformation. Here a permanent deformation takes place because of creep. So, although the yield point has not been crossed, although there is no plasticity as such which might be involved, still you have creep, meaning a creep strain which remaining behind in the product. So, that is something we need to guard against. And so, the life of the component, for example, you have certain tolerances given for certain dimensions, and because of creep over a period of time these dimensions get distorted or these dimensions increase, let us say. There is a strain in the component. Then as a result of that creep strain, the component has to be replaced because it is no longer able to function the same way as it should have functioned, or same way as it is designed to function. So, the life of the component can often be curtailed, not because it has yielded, but because it has acquired a certain creep strain after functioning for a prolonged period of time under high temperature and high stress. Now, some creep mechanisms, as has been said, is do not involve dislocation slip, and one of the classic examples of creep is the creep of the heating element in an incandescent lamp, where over a period of time it gets heated up and then it sags progressively due to creep, and so under its own weight it sags, and therefore after some certain duration of service at the service temperature, it will finally sag beyond limits, meaning it will break. So, that is how there is a creep damage getting accumulated in this filament. So, there are it is important in engineering applications like steam turbines in power plant, jet engines, nuclear reactors. So, typically the steam turbine blades have to withstand very high temperatures. So, even gas turbine blades have to withstand even higher temperatures, because steam turbines operate at much lower temperatures compared to gas turbines. In gas turbine power plants, the temperatures to be withstood are even higher, and then with the pressure acting on the turbine blade, the temperature, it is an excellent recipe for the turbine blades to change their size and shape. And so, beyond the limit, the turbine blade will become completely inefficient in converting the energy in the gas, high pressure gas, into power. So, essentially then the blades have to be changed because of the change in the blade angles or blade geometry as a result of creep. And creep is inevitable when it is exposed, when material is exposed to high temperature pressure for a duration of time. Jet engines, nuclear reactors. In nuclear reactors, you have an additional problem of the radiation damage taking place. So, radiation damage results in generation of vacancies, which encourages diffusion of atoms. So, there are many other factors which come into play in case of nuclear reactors. So, creep is aggravated or accelerated by virtue of nuclear damage, because radiation damage, because in the presence of vacancies, in the presence of defects generated by radiation damage, you have creep rate going up quite significantly. So, generally we have three stages of creep. One is, so this is the steady state creep which is of interest to us. The primary creep, which is the transient creep, which lasts for a very short period of time, but then here this is the most important zone. So, we need to widen this zone to the extent possible and not get into the tertiary creep region until the material ruptures. So, we have seen these the corresponding creep strains and the effect of stress and temperature. So, as stress and temperature or both increase, the creep rate also increase. So, the steady state creep is higher with at higher temperatures and higher stresses. So, here we see that the rupture life comes down as the stress increases, and also with increase in time. So, this is again because of the creep damage or the creep strain getting accumulated continuously, and after a certain time it would rupture. Now, you have creep strain rate under steady state. The creep strain rate continues to increase with time, and then for a given time the stress which can be withstood diminishes with increase in temperature, because then creep will become increasingly faster with an increase in temperature. So, at a smaller temperature the material can withstand higher stress for the same creep strain. So, since creep is something that happens over a long period of time, we need to understand the properties within a reasonable period of duration of testing. A tensile test, for example, might last for say 20 minutes, 25 minutes, half an hour, but then a creep test might last for several years. So, the creep strain which might be measurable can be generated over a long period of time of several months or several years also. Since we do not have so much time to wait and then get the results out, basically from application point of view we need to finish the creep test in a reasonable period of time, and that is the reason why we need accelerated creep tests. And so, we have different stress levels and different temperatures, and then we have rupture time for each of these creep tests. So, we test the materials at, let us say, 1000 degrees centigrade. So, 1000 MPa for 550 degrees centigrade, 650, 800 degrees centigrade, and so on, and calculate the or measure the rupture time that is needed for the sample to get damaged. Now, to bring together two of the three parameters, we have stress, time, and temperature. So, instead of having a 3-dimensional plot, we can generate a 2-dimensional plot only by combining the effects of temperature and time, because as temperature increases or as time increases, the effect on stress, as we saw in the previous graph here. So, as the time increases or temperature increases, the stress levels behave in a similar way. So, what we need to do is we can combine the effect of temperature and time. If the temperature is higher, time for rupture is lower. If temperature is lower, time for rupture is higher. So, as we see here from this creep rupture test also, for a given stress you have for a given stress for high temperature you have a smaller rupture time. For higher for 550 you have larger rupture time, and for 800 degrees centigrade it will rupture faster. So, the stress is lower and rupture is faster. So, what it means is that rupture time and rupture temperature, rupture time and temperature of testing both act in the same affect the stress, in the sense the stress gets reduced with increasing temperature, stress get reduced the stress capability gets reduced with increasing time. So, as the creep strain increases. So, that is the reason why we can combine the effects of temperature and rupture time into a Larson-Miller parameter, which is given here. And then when you plot this parameter in terms of C plus log of time to rupture, then where the time to rupture is in hours, okay, and C is constant at 20. So, one plots this in terms of 1000. So, this is 12,000, 16,000, 20,000, 28,000 and so on. So, the Larson-Miller parameter is plotted in terms of thousands into this. One can plot the stress here, and then you see three discrete zones in terms of rate of decrease of stress. So, the stress capability is reduced with increasing Larsen-Miller parameter. So, for a given Larsen-Miller, so it also means that if I have a Larsen-Miller parameter of 16,000, then various combinations of time and temperature and time to rupture, various combinations of temperature and time to rupture will which might give me the same Larsen-Miller parameter will result in the same one single value of stress capability. So, that is what it means. So, once the Larsen-Miller parameter is constant, there is the stress capability remains the same. So, that is the advantage of combining these two effects. So, that is why there is a one-to-one correspondence between the stress capability and the Larsen-Miller parameter, which is a combination of temperature and time to rupture. Now, comparatively, the strain that is recovered here differs between polymers, metals and ceramics. So, in polymers, practically the entire creep strain can be recovered, because the mechanism of deformation is different. You have chain molecules which can be which get extended, let us say, during the creep process, and then they can contract as the stress is brought down, and then you have a complete recovery of strain, recovery of creep strain. So, creep is not such a major problem in case of polymers, but for metals and ceramics the recovery is very little. So, so this is the final creep strain at the maximum load, but then when you release the load, not everything gets recovered, very little gets recovered here, and that is the reason why one needs more attention with metals and ceramics. Creep of metals and creep of ceramics requires greater attention because of the creep strain being retained to a substantial degree. The structural changes that take place during creep are diffusion related changes. So, there is lot of diffusion taking place because of time, temperature, activation energy type of processes operating in the material. So, the deformation at elevated temperatures is usually inhomogeneous, and as the temperature increases, dislocation slip decreases. I mean, the component of dislocation slip will reduce, subgrain formation will take place, and so recovery processes will start, and grain boundary sliding will become increasingly important as the temperature goes up, because as the temperature increases and exceeds the equicohesive temperature, then the grain boundary sliding will dominate the entire set of mechanisms. So, that is the reason why with increase in temperature, the three different mechanisms which are concurrently operating will change in terms of emphasis, or change in terms of contribution. So, formation of slip bands, multiple slip, grain boundary migration. So, these are also processes which depend upon the dislocation density of the material. For example, if the dislocation density is very high, then the grain boundary migration can take place. If there is a big difference between the grain sizes, then bigger grains will grow further in size at the expense of the smaller grains. So, different kinds of processes resulting in change in the grain size would take place during the course of creep. So, if you have very small grain size initially during the entire creep process, so there can be some growth in the grain size, but then on the whole the creep resistance comes down, the resistance to creep or strength under creep comes down with increase in temperature and increase in grain boundary area, because the grain boundary area becomes weaker, the grain boundary becomes weaker at high temperatures, and therefore most of the deformation gets concentrated in the grain boundaries, and so the resistance to deformation goes lower and lower as the grains become finer under creep conditions. So, so we need as large a grain size as possible so that the creep is resisted. Now, what we are looking at, the amount of creep strain, as I told earlier, is extremely small strain developing over a large period of time. So, we have about less than 1% strain rate of less than 1% per 1 lakh hours. Okay. So, basically 2.8 into 10 to the power minus 11 seconds inverse is the strain rate, I mean an order of magnitude of strain rate that is that can be tolerated. I am not saying expected, because expected is 0, but you cannot avoid creep strains at high temperatures and stresses. Therefore, the strain rate has to be maintained. Mind you, the loading is below the yield strength, the loading is below the yield point of the material, and so your creep strain rate has to be maintained below a value of, let us say 2.5, 2.8 into 10 to the power minus 11 seconds inverse, right. So, this is a strain rate which is a total outcome of various mechanisms operating concurrently. Now, different mechanisms and different slip systems can come into operation at high temperatures, or they can get activated at high temperatures. So, that is how the structural changes take place during creep. When you have dislocation slip taking place, then the Mg and Zn undergo non-basal slip. Normally, basal planes of the hexagonal close pack structure are one of the most favored planes for slip, particularly when the temperatures are relatively low. The slip system involving the basal planes of the HCP crystal are very active, but as the temperature increases and then different slip systems like non-basal, that is prismatic slip systems, get activated, and they are the ones which can take over. So, the resistance to flow will change, the resistance to plastic deformation or to creep deformation, not plastic deformation, to creep deformation will change depending upon the plane on which slipping is going to take place. So, similarly other slip systems such as 100, so these are not really favorable slip systems under normal. So, 110 is a favored slip system under room temperature conditions or low temperature conditions, but then some of the so called unfavorable planes also get activated above 200 degrees centigrade. So, basically those planes which are not favored, which are not really close packed planes in a face centered cubic crystal, can also get activated, because now mind you, you are not talking about dislocation movement or slip as a result of I mean the creep strain as a result of purely dislocation movement. There are many other mechanisms which are like diffusion, which are going to get activated, and so one can I mean the other slip systems which are not favorably or close packed, which are not as close packed as a 111 plane, can also get activated. So, non close packed planes and directions can also get activated only because of a high temperature. As the temperature increases, these planes would also get activated. So, increase in temperature it decreases the critical resolved shear stress. That is quite obvious, because we find that the material softens as the temperature is increased, and therefore the critical resolved shear stress also would come down. And so, with this you will get different other slip systems also getting activated. Then there is sub-grain formation, where lattice bending due to inhomogeneous deformation will take place. So, same size dislocations are created, same sign dislocations are created, formation of low angle grain boundaries due to easy climb and slip at high temperatures, which leads to formation of subgrain. So, as the deformation due to dislocation gets accumulated, same sign dislocations are created, then the subgrain boundaries are created, and these subgrain boundaries finally become grain boundaries of a very low angle. So, these subgrain boundaries get developed into low angle grain boundaries subsequent to recrystallization, and subgrain size depends on the stress and temperature. So, as the stress is more, okay, as the temperature increases, stress is lower, strain rate is lower, it produces larger subgrains. So, if the stress is more, strain rate is more, then the subgrain size would reduce, because the dislocation density will be more, the subgrain boundaries will be much closer to each other, and therefore, the size of a subgrain would be much less if in case of high stress and high strain rate. We have seen that the structural changes during creep include another phenomenon called as grain boundary sliding, where there is shear across the grain boundaries, and this grain gets displaced over with regard to the other. So, here you have created a deficiency of material, you have excess of material, and this is compensated by other mechanisms like diffusion, for example. So, that is the reason why the process is diffusion controlled. For example, if this is grain boundary sliding that is taking place, and then it introduces deficiency of material on one side and excess material on the other side, we need some transport mechanisms to maintain the continuity of the material, to prevent any discontinuities in the material from being created, and therefore, we need mechanisms like diffusion and grain boundary migration to take place, so that these deficiencies get bridged, these deficiencies get compensated for, material which was in excess here gets transported here. So, that is the kind of process. So, that is the reason why diffusion becomes the rate controlling process. So, the creep rate depends upon the rate of diffusion. Now, if you take materials like tungsten, refractory alloys like tungsten rhenium or molybdenum tungsten and so on. So, there the creep rate is so low because the diffusion is very small, the diffusivity of atoms is extremely small, diffusivity of solutes through the crystal structure is extremely small. So, these are all body centered cubic materials, the refractory materials are usually body centered cubic, be it tungsten, be it molybdenum, and these materials permit very little diffusivity through the lattice. And so, any mechanism that requires diffusion, because if you have grain boundary sliding, you need diffusion to take place to bridge this deficit. So, the rate of diffusion becomes the rate controlling mechanism of how fast the grain boundaries can slide, to what extent the grain boundaries can possibly slide. So, that is the reason why these refractory materials show high creep resistance. That is because diffusion is that much slower, and therefore, the creep rates are also extremely small in spite of high temperature and long durations of exposure. So, high temperatures and low strain rate promotes grain boundary sliding, and that is because at high temperatures you have the greater diffusion taking place, and therefore, grain boundary sliding also takes place, and more is the diffusion, and high temperatures grain boundaries are also much weaker. They have much less strength, and therefore, the strain at the grain boundary becomes higher, shearing becomes easier at the grain boundaries. So, that is why it promotes higher grain boundary sliding. On the other hand, if strain rate is higher, then you have viscous strengthening taking place at the grain boundaries, due to which you will not have so much of grain boundary sliding taking place, because the forces are countered by an increase in the local strain rate of grain boundary sliding, and the viscous effects will essentially increase the strength at the grain boundary. So, when the strain rates are relatively low, it promotes grain boundary sliding, because the grain boundaries remain relatively weak as compared to the interior of the grain, and that is also supported by an increase in temperature. So, diffusion and weakening of the grain boundary both are supported by increase in temperature. So, if the diffusion does not match the rate of grain boundary sliding at some point, then the fracture takes place, grain boundary fracture. So, in fact, the triple junction will start, because these three grains may start moving away, and then you will generate a void at this triple junction, which will propagate and finally end up as a failure. So, the grain boundary fracture finally will take place if the creep mechanisms do not operate in unison, or they don't compensate for each other adequately. So, if you take viscous creep, so increase in viscosity at the grain boundary would take place. I mean, it would vary depending on the temperature. So, this is the shear viscosity tau upon gamma dot shear stress divided by the shear strain rate, and the tensile viscosity analogously is sigma by epsilon dot. And if we take the viscosity in tension and in terms of viscosity under shear, the viscosity under tension is 3 times the viscosity in shear. So, that is what one can derive for ideal incompressible and viscous substances. So, you have some solids which behave similar to liquids with a high viscosity, like non-metallic materials like glasses and polymers, because the whole mechanism of deformation is different. Glass is a supercooled liquid and it is amorphous in nature, and therefore their behavior, I mean, you will have viscous effects which will be the only ones which will play a role in deformation of the glass or creep of these glasses at high temperatures. Similarly, polymers. Creep deformation involves time dependent movement of molecules or groups of molecules relative to each other under the applied stress. So, in particular in case of polymer type of materials, and thermal activation, which is in the form of diffusion process, follows the Arrhenius type law, which is something like this. So, this is the Q, which refers to the activation energy for that particular mechanism. So, Q takes the value of the operating mechanism. It is not a general value. It will, the value of Q at any given temperature and stress condition would be determined by the operating mechanism. So, if this Q of diffusion, for example, diffusion is the rate controlling mechanism or the major mechanism, you will have Q of diffusion. So, that is why we have different creep mechanisms and the corresponding equation and corresponding strain rates at different mechanisms. So, now we have creep in polymers also. The creep is significant above the glass transition temperature, and that is when the polymer tends to behave more like glass, and Tg of common polymers is 100 to 200 degrees centigrade, and so creep is often observed even at room temperature, but then at 100 to 200 degrees centigrade it is very significant. So, about Tg, hydrogen and van der Waals bonding is less effective. Molecular chains can slide past each other. In under room temperature conditions or low temperature conditions, these secondary forces or secondary bonds are quite strong, and therefore the sliding of the chains relative to each other, because in polymers you have macromolecules which are folded over each other, and so these molecular chains have to slide so as to deform. Now, if the ease of sliding increases by weakening of these hydrogen and van der Waals forces, then they can slide past each other, and the creep becomes easier in polymers with linear molecules without cross branching or without intertwining with respect to each other, because this interlocking can increase the creep resistance. So, if there are linear polymers without any branching, then you have much lesser resistance to creep. So, it all depends on whether you want it to creep or whether you want to build creep resistance into it. So, if you want to build strength into the polymer against creep, then you need to have branched polymers or cross-linked polymers which will have relatively stronger bonds with each other, even if the van der Waals forces and hydrogen bonds become weaker, still you have so many of them that that they can still pose a significant resistance to creep. So, creep rate dependence on sigma and T is roughly similar to viscous flow. If T is sufficiently high and obstacles for sliding are relatively weak, then the material will behave, the polymer for example will behave more like a viscous liquid. So, normally when we do molding, let us say polyvinyl chloride, PVC is known to be a viscous polymer. So, when you heat it, the polymeric chains are able to slide very efficient with respect to each other, and therefore, the polymer flows as a viscous liquid. So, the viscosity of the liquid is very high. Similarly, HDPE also will similarly flow when the temperature is increased, but its viscosity will be relatively low because of the nature of the molecular chains. So, depending on the chemical nature of the molecular chains of every polymer, you will have different degrees of viscosity, different magnitudes of viscosity at a given temperature. So, the creep rate at a given temperature will depend upon the stress and the viscosity that the polymer is able to generate. So, obstacles for sliding often acts as springs, that is creep deformation is partly recovered with time. So, basically if you remove the load, the spring will retract normally, right. If you remove the load, extension load on the spring or compression load on the spring will tend to come to its original position. So, the creep deformation also gets partially recovered with time. So, over a period of time, this creep deformation on which has taken place in a polymer can get recovered. In fact, often it is called as the memory of the shape of deformation, meaning that the shape that is taken by the polymer is something that was present before it was subjected to stress, temperature and creep related conditions. So, these polymers are often, we have said that almost the entire creep strain is recovered in case of polymers, it is recoverable in case of polymers, and that is because once the temperature reduces, then you have these bonds becoming stronger, the viscosity increasing, and the entire strain can get recovered as a result of a decrease in temperature. So, that is how the polymers differ from metals. Now, if you take crystalline materials, meaning crystalline alloys, metals and alloys, your steady state creep rate in crystalline materials can be given by A sigma raised to m upon d raised to q t exponential minus q by r t. We have already seen this q as activation energy for the operating mechanism. A is a material constant and sigma is the stress, m is the exponent of the stress. Now, d is the grain size, okay, and T is the absolute temperature. So, the strain rate depends upon, so smaller is the grain size, larger is the creep strain rate. So, that is the reason why we would like to make the grain size as large as possible to introduce as slow as strain rate as possible. So, depending on the mechanism, we have these constants m and q. So, diffusional creep, Nabarro-Herring creep is the creep deformation that takes place at very high temperatures, and so the proportionality is square of the grain size. So, it is proportional to square of the grain size, and also from low to medium level of stresses is something that you can expect diffusional creep, Nabarro-Herring creep. So, diffusion is a major contributor to the creep process. So, vacancy diffusion through the crystal lattice will take place, because vacancies are the ones which diffuse through crystal lattice. So, vacancy is actually something that is present at the grain boundary. What we mean by vacancy diffusion is that an atom moves to the vacancy at the grain boundary, creating a vacancy in the crystal lattice, which in turn attracts a neighboring atom, which gets into that vacancy, and then the vacancy therefore kind of diffuses through the crystal lattice from where it was generated, where it was born, to until it reaches the grain boundary once again. So, that is why we say that vacancy diffuses through the crystal lattice. Vacancies can also diffuse along the grain boundaries. Basically, grain boundaries are the regions of maximum disorder. The arrangement of atoms is not in an orderly manner, and so it promotes diffusion, because the atoms are at higher energy levels as well. So, the result is that the relative attraction between the two atoms, etc., can be overcome more easily, and therefore, the diffusion along grain boundaries also becomes very easy, and then you have so the dependence is cube. That is because diffusion along grain boundaries depends on the area of the grain boundary network. So, if the area of the grain boundary network is very high, then the diffusion paths are also relatively smaller, and therefore, vacancy diffusion along the grain boundaries, well, it will also take place at high temperatures, like diffusional creep in Nabarro-Herring creep. So, creep will always have vacancy diffusion along grain boundaries, but then at even higher temperatures it will have diffusion through the crystal lattice as well. So, let me put it that way, that vacancy diffusion along grain boundaries will always be present, but at higher temperatures the vacancy diffusion through the crystal lattice will also take place, because there is sufficient driving force in terms of temperature to allow diffusion of vacancies through the crystal lattice, through the grains basically. Then here you have dislocation creep, which occurs at relatively lower temperatures, and you have glide of dislocations with climb over obstacles. Now, the effect of temperature is dislocation climbing over obstacles, and since the temperature is not high enough to eliminate all dislocation activity, there is dislocation activity present. Now, the grain boundaries are not as weak as they are in case of, say, diffusional creep, that is Nabarro-Herring creep. So, because the temperatures are relatively lower, the dislocation activity is also present, and therefore, M is of the order of 3 to 8. So, the strain rate is significantly influenced by the stress and the corresponding dislocation activity, and then it becomes independent of grain size. So, the 0 is the value of Q. So, dislocation creep, or the so called power law creep, is entirely related with the dislocation movement, and it becomes independent of grain size, and so is the Harper-Dawn creep, which depends exclusively on dislocation climb. So, these are dislocation based motions, where or dislocation based creep deformation, and at any given point of time you can have more than one mechanism active. For example, at high temperatures you can have very small amount of say dislocation based creep. Most of it will be dominated by vacancy diffusion through the crystal lattice, but still you can have very small amount of dislocation activity. So, as the temperature increases, the contribution or proportion of dislocation activity decreases, and the proportion of diffusion related creep increases, or diffusion related mechanisms goes on being dominant. So, these mechanisms dominate at high temperatures. So, this is what I was telling in the previous slide. You start with the vacancy at the grain boundary, and then there is the so called vacancy sink, where the vacancies again come and get admitted, or they reach there. Similarly, so you have diffusion along the grain boundary. This is a situation in case of Koebel creep, which is a relatively low temperature creep. So, diffusion takes place along the grain boundary. So, vacancies move along the grain boundaries, and so smaller is the grain size, shorter is the diffusion path, larger is the grain size, larger will be the diffusion path. So, the grain boundary diffusion is much faster, much more effective in relatively low temperature creep, which is Koebel creep, and so grain boundary sliding takes place here. Grain boundary sliding will also take place over here. The grain boundary sliding will also take place over here, but then in addition to the diffusion along the grain boundaries, there is diffusion through the lattice as well in case of Nabarro herring creep. Now, the typical situation in creep is that or proof that there is grain boundary, relative grain boundary sliding, etc., is can be gauged from, let us say, 2 scratch marks. Let us say, so let us say originally the scratch marks were just made across this. Now, after a certain amount of creep, so the boundaries have moved. So, this was a continuous boundary dotted line. Here it has moved upwards. So, this reference mark has moved upwards, right, as a result of grain boundary sliding. So, you have made a scratch. So, this is a scratch which is made, and then because of sliding this scratch has moved. So, this reference mark which was continuous has become discontinuous. So, in case of creep related deformation, this discontinuity comes into play. Now, the next stage is what is called as superplasticity, where you have only grain boundary sliding, practically 100% grain boundary sliding. There is no dislocation activity at all, and that is where you need extremely fine grain size, extremely small grain boundary paths, so that the viscous effects are the ones which dominate the resistance to deformation, and any scratch or any damage gets evened out. So, there is absolutely no effect of inhomogeneous strain rate. The strain rate sensitivity is equal to 1 practically. So, that is the effect of grain boundary sliding. As the temperature continues to increase, the grain boundaries become increasingly viscous. So, we have the same thing which we had seen earlier. Now, when we come to power law creep, there are different models. So, we have Weightman's model where we say that the dislocation glide is aided by vacancy diffusion. Now, dislocation glide is facilitated by vacancy diffusion, because when an obstacle needs to be overcome, let us say this obstacle is present, normally this dislocation would get held up at this obstacle, and it will not be able to pass through unless it is able to circumvent that obstacle or cut through that obstacle. But now, because of the possibility of diffusion, these 1 or 2 atoms at the top can diffuse out, and then it can lead to dislocation climb, and once it has climbed by, let us say, one lattice parameter, then it can glide avoiding this obstacle. So, avoidance of the obstacle is facilitated by dislocation creep, where dislocation is the one, or dislocation moment is the one that governs the strain rate. So, the faster is the dislocation moment, faster is the strain rate, and the strain rate reduction due to the dislocation getting held up at an obstacle is prevented, or one can circumvent this obstacle by dislocation climb. Many times what happens is the interface between the obstacle and the matrix comes under heavy strain as the dislocations get piled up at that interface, and finally that interface itself gets damaged, and then the dislocation can circumvent the the obstacle and finally move forward. but that requires much more stress, that requires much bigger path, whereas here because of temperature the climb becomes easier, and then on a new plane the dislocation glides without any hindrance. So, that is how the strain rate is facilitated by the dislocation climb. So, if you want resistance to be built, then this dislocation climb will be counterproductive, because at high temperatures this climb would be much or very easy. So, in case of power law creep, the dislocation climb is the rate controlling mechanism, which means that if you are using the activation energy, you would use the activation energy for dislocation climb. If you are talking about Koebel creep or Navarro-Herring creep, then the activation energy for diffusion through the lattice or activation energy for diffusion along the grain boundary will have to be used for the Arrhenius equation. So, that is the difference it makes. So, the mechanism here involves dislocation climb as a rate controlling step. Earlier mechanisms involved diffusion as the rate controlling step. So, now because of that the stress becomes a very important parameter, because if the climb is not taking place, then the sensitivity to stress will be higher. But typically for power law creep, because there is also temperature present, 4.5 to 5 is the typical value of M. So, the strain rate dependence on stress is to the extent of power of 4.5 to 5. Another mechanism for creep is the Harper-Dawn creep at high temperatures and low value of sigma. Again it is observed in coarse grained aluminum and some minerals, ceramics, etc. So, this mechanism is slightly different. Creep rates are about 1000 times greater than those predicted by Navarro and Navarro-Herring creep. So, because of high temperatures you would expect Navarro-Herring creep mechanism to operate, because you have a sufficient driving force for dislocation, not dislocation, the vacancy diffusion along the grain boundaries and vacancy diffusion through the grain. But the creep rates are 1000 times more, meaning there is one more mechanism operating, which means that a dislocation climb mechanism is operational, which is aided by the vacancy migration. So, there is one more mechanism coming into play. In addition to vacancy diffusion, it is vacancy migration. So, when there is a compressive stress, vacancies are attracted to the dislocation line, dislocation moves upwards and opposite and opposite effect is found for the tensile stress, meaning the vacancies get repelled from the dislocation line, and so the dislocation can move, dislocation cannot move upwards, and therefore the creep resistance can increase. So, creep rate can reduce. So, basically what we are saying is that Harper-Dawn creep can explain the difference in the creep resistance under tension and compression. So, the creep rate under compression could be much greater than the creep rate under tension. So, here no grain boundaries are involved, and so it is independent of grain size. So, naturally, since it involves dislocations, it is so if your dislocations are getting attracted towards the vacancies and climb is aided by these by the vacancy migration, then the strain rate would go up, and so the sensitivity is between 1 to 3, and but usually it is strain rate is directly proportional to the stress applied, because you have dislocation climb which is aided by migration of the vacancies, and so basically it is a dislocation mechanism that is operational, dislocation climb being aided by the compressive state of stress and the dislocation getting vacancy getting attracted to the dislocation. Well, like many theories, you can have various opinions about it, but then one can definitely say that when there are number of mechanisms operating in parallel, one can think of Nabarro herring creep. Also, in addition to that, the vacancies while diffusing through the grain can also result in aiding dislocation climb, and therefore having a synergistic effect. So, the creep rate might not be explainable purely based on diffusion using Nabarro herring mechanism. So, this Harper-Dawn creep mechanism could be aiding the increase in the strain rate for a given level of stress. Now, dislocation glide alone is something that will need much higher stress, because now you are not talking about dislocation climb or something like that. So, you need very high stresses related to a shear modulus. The above certain stress, the steep dependence on strain rate on the applied stress comes into play, and so sometimes the sensitivity of strain rate to the stress increases significantly to the power of 10. So, the power law, the classical power law breaks down, means the dependency up to say 4.5 to 5 which we saw earlier. It is no longer valid because much higher stresses are needed in order to generate the kind of strain rate. The same deformation mode as in conventional plastic deformation at ambient temperature. So, here one would expect this at very low temperatures, because you have high stresses relative to shear modulus, and here the dislocation activity would be the maximum, very significant, and very little temperature effect or very little effect of diffusion related activities or diffusion related phenomena would be found at relatively low temperature. So, low temperature creep would essentially mean a creep by dislocation glide. So, this is these are the plots of the different creep mechanisms, and ln sigma versus ln epsilon epsilon dot has been plotted. So, you have dislocation creep which has 1 to 1, that is so it is proportional, and so okay. Even Harper-Dawn creep, you have m equal to 1 to 3. So, here also it is proportional to sigma, and then you have dislocation creep which is 3 to 8. So, the strain rate increases very rapidly. Why? Because now the dislocations can climb, dislocations can they can overcome the obstacles. So, for a relatively low stress, the strain rate can or a small change in stress, the strain rate can go up quite significantly. So, even if you have dislocation creep, by virtue of dislocation climb being facilitated, you get much higher strain rates. Now, if you look at the grain size effects, as a grain size effect, you have grain size increasing. Okay, as the grain size increases, the strain rate drops very dramatically, because the grain boundary area is reducing very significantly. So, see, if you have a certain radius of grain size, grain radius, the grain boundary area is going to decrease the square of the radius. So, as a result, you have very rapid decrease in the strain rates as the grain size changes. So, as the grain size increases, if the grain size becomes double, then the grain area becomes 1/4. So, the grain boundary area becomes 1/4. So, that is the reason why the diffusion controlled processes, Cobble and Nabarro herring creep, they get affected the most, whereas Harper-Dawn creep, which is independent of the grain size, continues irrespective of the grain size. So, here we have the Ashby-Weirtman maps, where we lay out different mechanisms. So, for homologous temperatures of up to 0.5 to 0.6, let us say, you have only elastic deformation up to the yield point. So, you have conventional plastic flow up to a point. So, maybe 40% of the 40% of the homologous temperature, or homologous temperature of 0.4, you have conventional plastic flow. At stresses, at higher stresses beyond 40%, let us say to 0.4 to 0.5 homologous temperature, at high stresses you have dislocation creep taking place. So, this is the situation where, let us say you have a boiler which is very heavily loaded, and it has and the stresses are little close to yield point. You see that there is a yield strength over here, and the stress which is being experienced is little lower than the yield strength, but very close to yield strength. So, you have what is called as dislocation creep taking place, and so as the temperature keeps on rising up to even 0.75 or so, you need much greater stress to cause dislocation creep. On the other hand, with increase in temperature, even at low stresses, there is enough heat, there is enough driving force for grain boundary diffusion to take place, as in case of Coble creep. So, Coble creep will occur at relatively low stresses, but temperature being the same and stress being high, you have dislocation creep taking place, aided by the vacancy diffusion. And then here you see that there is a bulk diffusion taking place at high temperatures and even low stresses, because you have bulk diffusion which is possible. The driving force is sufficiently large as to cause vacancy diffusion through the lattice. So, bulk diffusion means diffusion of vacancies through the lattice. So, here you have bulk diffusion even at higher stresses as well as the lower stresses. You have diffusional flow at high temperatures, low stresses, and then dislocation creep due to core diffusion, meaning diffusion along the grain boundaries and vacancies aiding the climb of dislocation. So, dislocation creep, but then dislocations are able to climb due to high stresses, vacancy migration due to high stresses, and due to some diffusional flow as well. So, with this we will see the mechanisms operating and for different kinds of materials, different kinds of strain rates, so silver, tungsten and so on, in the subsequent class. Thank you.